Okay, so you've all had a rough day, I guess. So I'm gonna end with some light entertainment here. There are no strategic interactions in this. It's all nice and simple. I figure, so we'll take it easy on you at the end of the day, right? So I'm going to talk about models of endogenous human capital formation and labor supply. And this is a joint paper with Payman, where's Payman? Yeah, there he is in the back, right? He can help me out if I screw up, right? And Payman is at UTS at Share, right? Traditionally, labor supply models always treated wages as exogenous, right? So the traditional labor supply models would treat wages as exogenously given. They follow some path with age, and that's it. More modern labor supply models are starting to treat wages as endogenous, determined by human capital accumulation. That when you start to think of wages as endogenous, it has important implications for how labor supply elasticities behave. It has important implications for optimal tax design, right? And we're interested in exploring those things. There are two main models of how human capital is accumulated. One is called the learning by doing model, right? And in the learning by doing model, it's very simple. When you supply labor today, you learn from that. You learn an amount that depends on how many hours you work, and that increases your wages in the future. There's also what's called the on-the-job training model, sometimes called the learning or doing model. And in these on-the-job training models, there are three uses of time. You either you spend a certain amount of time at work, and you have some time at leisure, but your time at work is split between productive work and time you spend learning. Yeah.
So just to be clear, you're saying this is still assuming that wages are equal to marginal product, and the marginal product is what the thought is.
Yes. Yeah. Now, what a big thing we're interested in here is looking at these two different kinds of learning models and asking if sort of life cycle labor supply behavior is different depending on which learning model you assume. Now, there's another aspect to this paper, which the question of how you treat wage shocks and taste shocks in these models, how you model them, the timing with which the shocks arrive. And there's this distinction in the dynamic structural literature between what I call Rust models, like Rust-Zerker style models, where you have the additive extreme value errors, and then what I call Wolpen models, where the Wolpen models don't have additive extreme value errors. The errors usually enter, they're usually not extreme value, they're usually normal or some combination of different distributions, and they enter non-linearly, right? Someone at a break earlier today said to me, "Oh, I thought all dynamic models had additive extreme value error." Right? So it's important, I guess, to see that they don't all have that structure, that some are different.
I finished PhD in my first lecture. So.
Oh, nice. Okay. There's actually a debate in this literature. there's these two papers by Blandon and Peterman, DaCosta Santos. These guys claim that which kind of human capital model you assume has very different implications for what labor supply elasticities are going to look like. All right. And we want to sort of kind of check who's right. So what we're going to do is we're going to estimate both an LBG and an OJT model, calibrate it to a ton of data, and then see if the models behave differently. We're also going to actually try to estimate you'll see later. I'm gonna try to estimate sort of what percentage of shocks are rust shocks and what percent are Wolpen shocks. So I thought of titling this paper "Rust Met Wolpen in a Bar" or something, but and the model is going to have discrete labor supply with continuous consumption, which I'm guessing Fedor talked about. Fedor? Yeah, you probably gave them a lecture on discrete continuous.
Oh, yes, yes.
Yeah, okay. So so this is going to be one of those. Okay.
Yes.
What were you listening to?
Broadcast.
Oh, okay. All right. So let me sort of describe the model. They're going to basically be, it's going to be the same model in all its features, except the human capital production function that'll differ. All right. So in the model, we're going to have 4 education groups, dropouts, high school graduates, people with some college and college graduates. There's going to be observed heterogeneity in people's initial human capital or skill endowment and in their preferences for leisure. As I said, they're going to have a continuous discrete choice set with continuous consumption and discrete choice of leisure. We're going to have 2 kinds of wage shocks. One occurs at the beginning of the period before you have to decide on your labor supply, and one occurs, and then so you get to see that shock before you decide how much to work. And then there's a second shock that's only revealed after the labor supply decision is made. Right? And like I said, we're going to have the 2 kinds of endogenous human capital model. Right? So the utility function looks like this, very simple. You get utility from consumption and leisure. We'll just assume it's log in consumption. Right? Then we have this term, a deterministic function of leisure, right? So that's this term here, right? So sigma is determining the curvature of the utility function in leisure as sigma gets larger, the utility. Let me think now. Was that running? That is in leisure, right? Not hours. Yeah, it is in leisure. Okay. So so this is determining the curvature of utility in leisure, sigma. And then at the end, we have these extreme value shocks, phi of L, that go with each particular level of labor supply you might choose. All right, there are going to be 4 levels of labor supply, so there's 4 possible levels of leisure L. Okay, so there's going to be 4 an independent extreme value shock associated with each level of leisure, right? And lambda is then the scaling parameter on that. Okay? So these are what I'll call the rust shocks. Okay. Now, as I was saying, in the learning by doing model, the hours of work H is simply 1 minus leisure. Right? Whereas in the on-the-job training model, it's more complicated. You have your leisure is 1 minus your hours of work is 1 minus your leisure minus your investment time or learning time. So now here's what the human capital production function looks like. So that we have K next period is equal to delta times your current K plus alpha times what I'll call I for a minute. Now I raised to the gamma and K raised to the nu. Now this I, depending on which of the two models you're talking about, in the learning by doing model, I is identical to your hours of work. Whereas in the on-the-job training model, I is the amount of learning time you choose. Now, the one thing I just realized is I don't think we have a slide for this, but a fundamental difference between these two models is that in the learning by doing model, you can actually see people's wage rate. You can look at the data, see the wage rate, and that is the wage that they're earning per hour of work. Right? But that's not true in the on-the-job training model. In the on-the-job training model, you're splitting your time at work between productive time and learning time. And the idea of these models is you're only getting paid for the productive time. Okay. But then when we look at data, what we get to see is the total, the amount you're paid for that productive time. But we don't get to see in data how many productive hours you worked versus how many learning hours you spent at work, right? We only get to see the total, right? So then when we take the ratio, we're getting the wrong wage rate. Like that ratio doesn't even mean anything, right? So the wage we see in the data is like incorrect because it has the wrong denominator, right? Does that make sense? Yeah. No, in these models, you're literally assuming that the work time is split, okay, between production and learning. Okay. Okay. Now here, we're going to assume that your wage rate is equal to how much human capital you have, K, right? So here, remember, human capital is K. The wage rate is just human capital K times the rental rate on human capital, right? Now, if this were an equilibrium model, the rental rate on human capital would be determined in equilibrium, but this is simply going to be a partial equilibrium model when we're going to normalize R to 1. And then we have the exponential, and we have two shocks, the epsilon sub W and the epsilon sub R, all right? So these are two productivity shocks. The first of which I'm calling the Wolpen shock, the second of which I'm calling the Rust shock, all right? So the idea is that the Wolpen shock will be revealed before you make your labor supply decision. So you get to see this when you're deciding. And the Rust shock is only observed after you make your labor supply decision. Now, why do I call them that? Well, if I got rid of these Wolpen shocks and assumed everything's a Rush shock, right? So I assume it's only observed after you make your labor supply decision. All right. Then when we look back at this utility function here, when you're making your labor supply decision, you would be constructing an expected value of every choice based on an expected value of the Rush shock, right? So those Rush shocks that would get integrated out, and you'd be actually, anyway, I'd be left with just these. So I would have nothing but extreme value errors. Now, on the other hand, if oops, wrong one. If we have these W shocks in there, things get much more complicated. Because then, then I have this additional shock that that's gonna affect my probabilities of choosing the different levels of work. So I will not get like a logit choice probability function, right? So I'll then have to form integrals over these W shocks to get the choice probability. Right?
Mike, are you calling a normally distributed shock a Rush shock?
Yeah, I just realized that's wrong, right? I've got because I'm using the term Rush shock for two different things, right? But the logic of it would be that if John were to write a model down, right, he would have shocks like that he would assume you don't get to see until after you've made your labor supply choice, right? And then that would enable him to kind of get rid of them, right? And then when he went to construct his choice probabilities, he'd only have to worry about these here, right? The extreme value shocks, right? Whereas obviously now if we have these that are at the point you're making the choice, right? So the agent knows what that W is at the time he's deciding. Because we as an econometrician do not see it. That's the complication, right? So if we assume the agent knows this, but we as the econometrician don't, right? Then to form choice probabilities, we have to integrate over what the agent might be observing here. Whereas John's timing assumption gets rid of that, makes it simpler, right? What we're gonna now, if you think about it, we're going to try to estimate the variance of both of these shocks, right? And they have implications, important implications for labor supply elasticities, right? Which actually have not been explored in the literature, right? Because the models basically assume one or the other, right? But if you only have the R shocks, right, and you don't have the W shocks, then transition rates will look quite different. So transition rates between employment states will look quite different depending on the relative importance of the R and the W shocks. That's the idea, all right? Okay. So So this is just laying out the timing of the model, which is basically what I've just been talking about. So first the W shock is revealed, then the taste shock is revealed. Then you make your labor supply decision, right? Then the R shock is revealed, then you make your consumption decision. So that's what's actually important here. Everything else is details, right? So now I'm just going to go through the other parts of the model, right? Does anyone have any questions on that stuff? Yeah. We don't look at that, but it's a good idea, right? Yeah. You'd obviously think this would differ depending on the nature of the industry, wouldn't you? So that's worth looking at. But we haven't gotten to that yet. Anything else? Okay, so the way we set this up, there's an unemployment benefit in the model. There's a Social Security benefit people get after age 65. The unemployment benefit is specified as a simple function of your human capital level. The Social Security benefit is also a very simple function of your human capital level. There's a tax function. So people in the model pay income taxes modeled after the U.S. tax structure. I think it's like in 2014. Right? So we have progressive income taxes based on the 2014 tax structure. We've also got the Social Security tax, the payroll taxes. Right? So as the unemployment benefit, it depends on both your human capital level and your education level, right? Here's the asset transition function. Payman, what is the P? Minus P. Is that supposed to be taxes? Looks like it should be taxes, right? T. Yeah, it probably should be T. Oh, well, let me see. No, taxes are in TR. So is P something else, or is it just? What's that? Anyway, we can get back to it. So again, the interest rate, if this were an equilibrium model, be determined in equilibrium, we're just going to fix it at 5%, right? Okay. Now, a problem. This model generates that people have. This model will generate life cycle hours paths, and it'll generate that as people's wages decline as they get older, because their human capital starts to depreciate. It'll generate drops in labor supply. You see what a key thing in these models is as you approach the end of your life, the incentive to invest in human capital declines because you're getting closer to the terminal period, right? So as people get into their 50s and 60s, they invest less in human capital. They have less of an incentive to invest in human capital, and that generates the wage declines, And that generates what looks like retirement behavior where people start working less. But a typical thing I always seem to find, other people seem to find in these models, is you can't quite get hours dropping quick enough in the 60s, just based on that. So we introduce some age effects in the taste for leisure, right? You start to make it more painful to work after you reach age 62 here. We have bequests. Okay, so in this model, people get utility from leaving bequests. That's actually quite important in these dynamic models because you need to do something to enforce that people don't just, borrow unlimited amounts of money and then die. So the bequest function prevents that. All right. Now, in terms of, as I said, consumption's continuous, but we're going to assume labor supply is one of 4 levels. Right. So we normalize the total time endowment to 1, and people can either work 1/3, 2/3, or 100% of it. I think 100% corresponds to like 2,400 hours. More than that, 2,600 hours. Okay. All right. Now in the on-the-job training model, they also have to choose what fraction of their time to spend learning. At this point, we have to make a decision. Do we want to make that a continuous choice or a discrete choice? Right. And I actually think that a model with continuous consumption, continuous investment, and discrete leisure would be harder, right? So it's simpler to make this additional choice discrete. So we actually discretize the potential learning levels. Okay. Now, so that's really, so it's a very simple model. That's all there is to it. Okay. What was that?
Pension what?
No pensions. No, it's the Social Security isn't really Social Security, right? I mean, we're not modeling the actual Social Security rules. We're just sort of saying you get. I think, isn't that right? It's Social Security plus pensions and so on. And we're just trying to fit the overall level of benefits as a function of human capital. Right? Now, we have to now solve for the optimal consumption. Okay. So these equations have to be satisfied, right? So the marginal utility of consumption today has to equal minus the discount rate times the derivative of next period's value function with respect to next period's assets times the derivative of how next period's assets are affected by current consumption, right? So that becomes the -1 plus R, and then we get that this equation has to be satisfied at the solution, right? and we have to find the solution to this equation at every point in the state space. Okay. So the next few slides are just describing how we do that. It's a really trivial algorithm. Let me just say that as Fedor probably talked about, in these discrete continuous models, you have to worry about this derivative being continuous. Right? It's potentially discontinuous, but in order to deal with that, we're just gonna smooth out. We're just gonna crank up the smoothing parameter enough to make it continuous. Right? So this is just a picture of how the consumption policy function as a function of assets looks for different levels of the lambda. Right? Remember, lambda was the scale of the extreme value shocks in the utility function. Right? So what's drawn here, I mean, this is a picture of what the consumption policy function might look like several periods back from the terminal period, right? If you hadn't smoothed. Okay. So you might get a picture like this, where as assets are increasing, you reach these points where you want to, where if your assets pass some threshold, you want to work less and consume less, right? And you've got multiple jumps like that because you're several periods from the end, and you might be when you're crossing these asset thresholds, you might be deciding to consume less, not just this, to work less, not just this period, but in future periods, right? So you get all these jumps. So what we're showing you here is how in cranking up the lambda smooths this out. And we're picking lambda around somewhere around 0.2 to 0.3, which the picture shows is good enough. Okay, so oops, now I can't go back. Oh, repeat, but I want to go back to before all that. Okay. So how do I press that? Yeah. With the mouse. Okay. Oh, there it is. Okay. But I can't go back before the first iteration? Oh, okay. All right. Okay, here. So no. I'm too old to learn anything. That's the problem. Now, so what I'm trying to show you is that in order to smooth out this derivative, we've cranked up the lambda, right? So now we just have to find the level of consumption at every point in the state space that will set this to 0, right? Or approximately to 0. Now one trick you can use in solving these models is that in these life cycle models, people generally want to smooth consumption, right? So next period's consumption. So as you're solving backwards, right? The optimal consumption next period that you've already solved for is usually a pretty good guess for what optimal consumption is going to be when you go one period back and you're in a similar state point, right? So what we do is just a trivial algorithm where we start by guessing that the solution is whatever the solution is next period, just hold consumption equal, right? And then, just so we plug in So plug in that particular value of consumption, the next period consumption, then look at how, you know, whether this thing is positive or negative. And then simply do some naive thing where you either increment consumption up a little bit or increment it down a little bit. Right? And then just keep moving them up and down until it converges. Right? And that is what, so this is where that's what it's doing. The Fedor likes pretty pictures like this. Yeah. So that's just for you. Okay. Okay. Now, okay. Now we're now gonna estimate this model using the method of simulated moments and using information from 3 different data sets. Right. And this is an important point for people to know who want to do empirical work using these models, which is that the sort of beauty of the method of simulated moments is that you can you know, often it's the case that you don't have all the information you need in just one data set, right? But the method of simulated moments easily allows you to combine moments from many different data sets. And that's what we're doing here. And that point's just for John. Who really emphasized this in the McFadden honorary issue when he discussed this point. Right? It's a really important advantage of method of simulated moments that you can do this. So let me just show you the stuff we're fitting. So from the current population survey, we're going to take data on employment, right? Employment rates, whether people are employment rates by age, by education, right? Average annual hours, conditional on working, median full-time hourly wages, again, conditional on age, education, and so forth. Standard deviation of the log of the hourly wage rate. So we're going to get some information on dispersion in wages, transition rates, the probability of working conditional on working last year, the probability of working conditional on not working last year. So the CPS has all this sort of data, but you know, the CPS, you can only observe people at best 2 times. You know, one year and then the next year. So it's so for instance, it's useless if you want to know anything about persistence in wages. Right? So then we go to the PSID, where people are tracked for many years, and we can use that to get information on wage persistence, right? So in the PSID, we can do a regression of log wages on some polynomial in age, get the wage residuals, and then look at the autocorrelations of those residuals at many different year lags, right? And try to fit that whole lag structure, right? Also in the PSID, you can see people's work experience, right? Which you can't see in the CPS. So using data from the PSID, we're able to construct moments for things like employment conditional on experience, annual hours conditional on experience, wages conditional on experience, right? Whereas, you know, in the CPS, you can only condition on age and education. Oh, wait a second. Where did? And then, and then finally, you know, neither of those data sets has very good information on assets. So to get good information on assets, you can go to the consumer expenditure survey. And to get, so from the consumer expenditure survey, you can get good data on consumption and assets and also fit moments based on those. Okay. So as I say, this is the nice thing about the method simulated moments. You can easily combine all these moments from different data sets together. And that's what we're going to do, and just, you know, try to minimize this simple MSM objective function. Right. Yeah.
What do you think of the moments that allow you to, identify the relative importance of flexible?
I think it's the transition rates, right? Because transition rates are much lower if you're basing your decision on expected wages. All right. So you basically, the more weight you put on the Wolpen type shock, the higher the transition rates become. And so that's the key factor. Yeah.
In simulation, we use more particular distribution.
What? Say that again?
We need to draw of a particular distribution, like no standard normal.
Yeah. So the wage shocks are normal, right?
Now I'm just wondering, are you able to draw the more generally without knowing that? Not only knowing the moment.
Well, let me. I'm not sure but there's a large literature in labor economics arguing that wage errors are approximately log normal, right? So when you take the log of wages, you know, Heckman had a paper years ago where he argued this, that the wage residuals really do look approximately normal in the log wage equation, right? You know, see, this is one reason we're talking about this, because those residuals, it's not going to work to assume their extreme value, right? That would be a bad approximation. You want to assume they're normal, right?
Another difference, I think, between the working model and the drug model
Mm.
is that the estimation of the log wage equation in the working model, there is selection.
Right. Right.
But not in the
Right. Good point. Right. I think there would still be selection, even if you were basing decisions on expected wages, right? It'd be a different type of selection and probably much less selection, but you'd still have selection, right? Because you'd still get the situation that you're more likely to see a guy working if he has a higher expected wage. But that's an excellent point, that that the nature of selection is going to be very different between the two models, right? Yep.
Quick question. So logging the data you're using, but suppose you had panel data in a PSID, and suppose you would use the panel for consumption and assets. I know it's not good, but the question is identification. Is something correctly actually identify, because of the differences in timing, the residual shock distribution? It might be the case if you had the whole sequence in a panel data
Oh, you're thinking that the timing of consumption
Yeah.
is also telling you about the relative importance of these shocks.
I think so, so
Hmm.
it's obviously not great data, but.
Yeah,
Just in terms of identification, you know, that you could get some consumption, you know, food consumption, but.
Hmm.
Food consumption data is so massive. If you use the whole panel, you might be able to semi-parametrically, again, I don't know.
yeah, yeah. Yeah, I have to think about that. That's a good point. Okay, so so when you put all this together, whoops, basically we've got roughly 340 moments that we're fitting for each of these 4 education groups. Okay, and when we do the estimation, we're gonna other than let's see, other than the human capital production functions, we're going to mostly constrain the other parameters of the model to be the same between the 2 models. Right? Is that a payment? Is that exactly? Is there actually nothing that differs? Just okay, just initial human capital and the human capital production functions. Okay. That's actually pretty incredible. Because as I'll show you in a minute, the 2 models give almost exactly the same fit to the data. The 2 models are almost indistinguishable, right? And that's not being achieved by, you know, moving around all sorts of utility function parameters to sop up differences. You're telling me everything's identical. Okay, that's quite amazing. Okay, so here are the parameters of the human capital production function. Okay, so so you can see it. So the key you can remember there is the function written down in the bottom. Now notice if you don't work at all, or you don't spend any time learning, right, then this term I is 0, this term goes away, and all you've got is delta times K, right? So delta is telling you how much your human capital depreciates if you don't work at all, okay? And you can see from these estimates that delta comes out at about 0.9 for the dropout high school and some college groups, and it's a bit lower for the college group. Okay, so the estimates are saying that the depreciation of your human capital if you don't work at all is somewhat higher for the more educated people. Okay. Now and if you compare the LBD parameters on the left with the on-the-job training parameters on the right, you can see that the depreciation rates are less in the OJT model. These numbers are all shifted up. Basically, they're all shifted up by about 0.02. So the depreciation is a little bit less. Right. Now, the other 3 parameters are hard to interpret, right? So it's easier to show you a picture. And so here's a picture of what the production functions look like, right? So so here on the left in the here's the learning by doing model. This is just showing you for high school people, okay? As I was saying, if you don't work at all, your wage is going to drop by about 10%. So this is wage growth. Human capital growth, wage growth are the same thing here. So wage growth on the vertical axis. If remember you either work 0, 1/3, 2/3, or 100% of the time, where the full amount of time is defined, I guess, is 2,600 hours. Right? And if you look carefully, you see that you have to at least you have to work at least 1/3 or maybe 2/3 of the time to prevent your wage from falling. And then there's a big gain here from working 1/3 of the time, but then this function is concave, right? So there's diminishing returns to this time spent learning. Right? Now, there are 3 different lines here because they're drawn for 3 different levels of human capital at the start of the period, right? And the hard to read, but the blue line is for a low level of initial human capital. The yellow line is for a high level of initial human capital, right? So you see also that as your initial level of human capital is higher, your gains to learning are diminishing. Both of those patterns are important because I've been doing other work where I plug these sorts of functions into DSGE models and then try to calculate optimal taxes, right? And if these things are not concave enough, you get really screwy things happening in those models, right? So now, if you go over here on the right, this is the on-the-job training model, right? And again, that model implies that if you devote 0 time to learning at the job, then your wage is going to drop about 8%. Right? I think that's about 0.92 there. And there's a big gain to devoting 10% of your time to learning, and then it diminishes rather quickly after that. Any questions about these functions? How's the time, by the way?
About 35 minutes.
35 minutes, okay. Okay. Now, these are the other parameters of the model, okay? And so the way this table is written, we have the LBD model on the left, the OJT model on the right, but if you look, you'll see that everything on the right is identical to everything on the left, right? So we're not allowing any of these parameters here to differ between the 2 models. Okay? So the utility function parameters are identical. The fraction of variance due to the 2 kinds of wage shocks are identical. Taste for leisure functions identical. The bequest functions identical. Right. Now, let me see here. So I'm trying to find where we report the wage variances. Is that? Yeah. B0. This here. Oh, okay. So what? This is the percentage of variance. Oh, okay. So it's 0.6. Oh, so John, you win. It's so so it's 60% weight on the rust shock. Oh, wow. Okay. All right. I won't tell Ken.
That's
All right.
not including the strip bar.
What's that?
That's not including the strip bar.
That's right. That's right. This is just of the two wage shocks. What percentage? So, and notice, actually, I should have said, this is a good point, right? It's rising with education. So it does differ by the type of job you have, right? And wow, so for the college people, it's quite high, right? Now, what's driving that is you're better able to match transition rates, right? You know, Fedor, how we had all this trouble matching transition rates? Well, if it's really hard to get the persistence in these models. And people have found this for years, that these dynamic labor supply models tend to underestimate persistence in staying at jobs, right? And so we're able to generate more persistence by shifting more of the weight onto rust shock. So.
What about a job also you have like creating that system there, but you have to sort of then
So you want to augment the model to just have fixed costs of moving. Yeah. 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 I mean, obviously you could build that in, and then then we'd have to think about what would separately identify these moving costs, right? So anyway, I haven't thought about that yet. We'll have to think about that, right? Okay. Now, this is the so this is the heterogeneity parameters. As I said, we have heterogeneity in the taste for work parameters, where there are 3 different types, and there's heterogeneity in initial human capital, right? So there's like a low skill type and a high skill type within each education group, right? And these heterogeneities, the heterogeneity in tastes is also constrained to be the same between the 2 models, right? So the only other thing that differs between the 2 models is the heterogeneity in initial skill levels, right? Okay. But that pretty much has to be the case. Those have to be different because you're plugging them into fundamentally different functions, one of which has learning time here, the other one has hours of work here, right? So these initial Ks have to adjust because the other parameters of that function are different. Okay. All right. So following here are a bunch of slides about the model fit. Now, we're still working on the fit to consumption. I think Payman has told me that the computer's running right now on models that actually fit this a lot better. Right, so the consumption fit actually is improving as we iterate here. If you look at if you look at the pattern of, this is for high school people in the learning by doing model. The fit to work by age, the fit to hours conditional of work by age. Those look pretty good. The fit to these things against experience, that doesn't look quite as good, but I believe we can fix that by adding a third type, an additional skill type. Because the reason for this drop off is that the lower skill types are retiring sooner than the higher skill types. So if we add a third type that's in the middle, we can just smooth that out. That's probably actually a useful stuff for you guys to hear, right? You know, you have to get a sense of how you improve these models, right? So you have to think about why they're not fitting, right? And here it's pretty clear why that's not fitting. That for this is the, you can see this is the first type. Anyway, now is this so this payment, this is the LBD. Oh, then it's going to be okay. I see. Okay. So, okay, consumption, work, where are wages? Oh, where? Ah, damn it. Oh, sorry, I screwed up. I keep going the wrong direction. Work, consumption, work. Okay, here are transition rates. And if you look at the transition rate from not working to working, this is actually quite a good fit. If you look at these sorts of models that people have done in the past, as I say, they have a lot of trouble matching transition rates. That's quite a bit better than you'll typically see. Now, okay, here's the fit to life cycle wage paths. This is wages against age on the top, wages against experience on the bottom. This is the persistence in wages. Okay, so this is the autocorrelation function as it dies off, as you lag wages. This is the standard deviation of wages by age, and it's not quite right, but it matches the path reasonably well. Now, everything up here is the LBD model, and then following that is the OJT model. Now, so if you guys, oops, okay, right. If you guys can remember the LBD slides, this is what's tough. These slides look almost identical. Right? So when you go through the OJT slides, everything looks almost identical to the LBD slides. I don't know, do people have a good enough visual memory that you can like, I'll go through so I'll go through them again. Here's LBD, 1, 2, 3, and here's the other one. You wanted me to go on the bottom? Anyway, but they are the same, trust me. It's remarkable how these models fit the data almost exactly the same. Now, okay, now let's get to the interesting part. So, and we're actually almost done, right? So, how much time's left, you know? Really? Okay. All right. So one of the big reasons we wanted to look at these models was to see whether or not they have different implications for labor supply elasticity. Okay. So what we're going to do now is simulate what happens if you reduce wages by 10%. Right. Now, the first one I'm going to show you is we're going to look at high school people, and we're going to have an anticipated permanent wage reduction of 10%. Right. And I think the way this works is that the wage reduction happens either at age 22 or 30 or 40, or is it? It's okay, but so if there's a permanent lifetime wage reduction of 10% from age 22 for the rest of your life, right? So basically this person's being born into a new world where the tax rate is 10% higher. Now, what these bars are showing is what happens to their different uses of time. Okay, so the purple bar is the change in leisure in the LBD model, and the green bar is the change in leisure in the LOD or OJT model, right? And you see that they're almost identical. So the 10% permanent wage reduction at age 22 causes roughly a 10% increase in leisure in both models, right? And you can see if you go at different ages, right, that the effect on leisure is almost identical at every age. Right? The only thing I'm not sure about is when you look at, say, age 40, does that refer to a permanent tax increase that happens right at 40? Or was it in effect their whole life? Okay, so it happens at 40, but when they were born, they knew it was going to happen. So that's a sense in which it's anticipated. Okay. Now, so these two models, these two different human capital investment models, generate essentially identical leisure responses to this tax change. Okay. Now, how else might they differ? Well, the red and blue bars, so red blue are the first two bars. Those refer to your total time at work. So in the LBD model, that's just total time at work. In the OJT model, total time at work is your productive time plus your learning time, right? And and if you look at the red and blue bars, you again see they're almost identical, right? So the two models are generating almost identical responses to total time at work. Of course, that's equivalent to saying they generate same leisure response, right? Now, the difference in the OJT model is you get a couple more bars, right? You get the yellow bar is telling you what's happening to productive time at work, and this blue bar here is telling you what's happening to learning time, right? Now, there you get a kind of interesting pattern that at age 22, the productive hours at work drop and the learning hours go up a little bit. All right. But then if the same sort of permanent tax increase happens at a later age, it's different. At later ages, as soon as you're 30 or more, the learning hours drop. So you get this distinction that for very young people, this tax increase causes learning hours to go up a little bit and productive hours to drop. Afterwards, they both drop. But in terms of everything you can actually see in the data, right? At least data we typically have, we can't measure learning hours, right? So you can't, so in terms of everything you can actually see, the models look identical. So here's another slide. The only difference now is that it's unanticipated. Okay. Again, the bars look quite similar, right? Notice that the overall, the effects are smaller, right? Now that's typically what you'd expect in these models. If the change at, say, age 40 were anticipated when you were born, you can plan your whole life cycle consumption path, leisure path, based on knowing this is going to happen at 40, right? So therefore, you expect a bigger response than in the scenario where it comes as a surprise to you at age 40. And in fact, you see it's a much bigger response, right? Now, now we turn to transitory shocks, okay? So if we look at anticipated transitory shocks, again, the purple and green lines, which are telling you total leisure time, right? They look almost identical, right? So the effect of anticipated transitory shocks on leisure is pretty much identical between the two models. Comparing the total hours, that's just the flip side of that. So again, they look pretty much the same. Now here, it's kind of interesting. If you look at the effect on learning time, right? If you have a transitory wage reduction at age 22, you see that your response is to have a big reduction in production time and a big increase in learning time. All right. So that's an interesting contrast between the two models, right? The OJT model says that if you have a transitorily low wage when you're young, that you'll say, okay, well, this is a good time to be learning. So I'll shift out of production time into learning time. Now notice, once you're about age 40, in fact, once you're up to 50, that effect is gone, right? So as you get older, if this transitory low wage happens when you're 40 or 50, your productive time goes down and your learning time hardly changes. So there's an interesting life cycle path to how you respond. And then on an unanticipated transitory is actually pretty similar. Now, in some ways, this is easier to see in a table. So here's just a table, minus 10% anticipated permanent wage shocks happening at different ages This is just, this is a table of the labor supply response, different education levels, comparing the two different models, and just looking at those numbers, you can see how close these models are. Now, one thing you notice here is that both models imply that the elasticity of leisure with respect to wage changes grows substantially with age. Okay. And that's a very important point, right? So traditional labor supply models that don't have human capital, that treat the wage as exogenous, right? In those models, the labor supply response is completely governed by the parameter in the utility function on leisure. So remember, we had leisure to the sigma power. The labor supply response in those simple models is completely governed by sigma, right? And therefore, since it's governed by a single parameter, it's a constant. It doesn't matter what age you are, okay? Whereas these human capital models, they all generate this pattern that elasticities grow substantially with age, and they get very large for old people, all right? And the intuition for this is really simple. When you're young, the wage is a relatively small fraction of your return to working, right? The learning return is very important, right? As a result, if I tax away a bit of your wage, right, that actually doesn't reduce my return to working very much, because when I'm young, so much of the return to working is the return from learning, right? Now, when you get old, you're near the end of the planning horizon, there's just no return to working anymore, no return to learning anymore. The whole return to work is the wage rate, right? I hit the wage rate with a tax and I'm going to get the full response to that, okay? Now these sorts of patterns have really important implications for optimal tax policy, right? Because these have optimal tax models essentially say you want to tax stuff that can't move, right? You want to tax things that are inelastic, right? So you see patterns like this, it implies you should sort of create time paths in taxation to hit the people with the lower elasticities with higher taxes, right? So so I don't have anything. That's what we're working on in some other work that I don't have here to show you. Okay. So I can just, here's unanticipated permanent wage shocks. You see the same, two models are very similar. Again, the elasticities become substantial at older ages. Here are anticipated transitory wage shocks, same pattern, elasticities growing with ages, and unanticipated transitory wage shocks, same pattern. Right. Okay, and the remaining slides are just appendices. Okay, so I'll just leave it at that. And if anyone has any questions. What's that?
So the conclusion is we can use either one of the models.
Well, the interesting question, these models, as I say, they generate, seemingly equivalent fits to the data. They seemingly generate same labor supply elasticity patterns. There is a question, okay, is there something else that might differ between the two models? So Jim Heckman has a paper where he argues that the response to an earned income tax credit differs between these two models. So that's something we need to test. Right? So we can take these two models, we can do an experiment where we introduce an earned income tax credit and see if people respond differently in the two models. All right. But I think, and I don't know what'll happen. We haven't done this yet. Right. But obviously the two models are, if they're different, it's very subtle. So it's I don't know like what statistical test you could ever use to distinguish between these two models.
They're not nested, right?
They're not nested. Yeah. So the distinction finding a data pattern that would clearly distinguish them is not easy, precisely because of the fact that as I was saying back here, what the only real difference between these two models is that the change in learning time versus production time. And in data, you can't typically see that. I guess if you could actually get data that measured learning time and production time, then maybe you could. But even then, that doesn't. As an abstraction, I mean, suppose we could figure out that at work people really do spend a certain amount of time learning and a certain amount of time producing, right? Suppose we could somehow discern that that's the truth. Would modeling that matter for predicting effects of taxes on labor supply? It's not clear. Everyone's tired by now, I assume. So we should.
Just to get to understand, so you are able to estimate, identify the two types of observed shock, right? And that's because you can flow from that in simulation. And also, in other words, if you don't use simulation, are you able to separate?
Well, as I said, I think the fundamental difference is that if we say that people observe these wage shocks prior to making labor supply decisions, okay, so if we only had the W shocks and not the R shocks, right, we would get transition rates that are much too high. So you would see people, you would see people shifting between the different levels of hours much too often. Because they can see, because they're responding immediately to these wage changes. By taking the weight off the W shock and putting it on the R shock, you're able to get people moving less between the hours level. And that fits the data better.